Hi, I'm Piyush Jain and I'm a software engineer at YugabyteDB working on the core DB. My colleague Rob and I are going to talk about PostgreSQL compatibility. Now, it's a very vast topic, but what we'll try to do is focus on two new enhancements that we have in YugabyteDB in the transactional layer. And these two enhancements help YugabyteDB come close to Postgres in terms of transactions, right? So the first enhancement is read committed isolation. It's a new isolation level that we are adding to YugabyteDB. This is also the default isolation level in Postgres, and adding this isolation level brings Yugabyte in parity with Postgres. What I mean by this is Yugabyte is going to have all three isolation levels that Postgres also has, right? Now, apart from this, the second enhancement is pessimistic locking. Now, what pessimistic locking does is it helps Yugabyte match the semantics of Postgres when there are conflicting transactions. So without pessimistic locking right now, Yugabyte is optimistic in the sense what it does is if there are conflicting transactions, they're going to abort each other to make progress, right? But what Postgres does is when a transaction conflicts with other transactions, it is going to wait for the other transactions to end by either committing or rolling back, and it is going to make progress itself as is appropriate, right? So this leads to lesser aborts due to conflicts, and matching these semantics ensures that users see the same externally visible behaviors, right, when transactions conflict, and it also gets us, better performance in some workloads, right? So that is pessimistic locking. Now, having said that, both of these are just enhancements. These don't change the strong consistency guarantees or isolation level guarantees that exist today, right? So moving on, we talk about compatibility, but why is it so important, right? So if I were an user, I wouldn't, so let's say I wanted to scale my app to a distributed database to get, all benefits of horizontal scalability, fault tolerance, etc., etc. And if I were to do that, I wouldn't want to rewrite my app in any way for it to work with the distributed database, right? I don't want to spend time and energy on that. So that is why compatibility is important, and I mean it should just work right out of the box, right? So I mean that's why compatibility is important, right? So given that it is important, like different distributed databases which try to be compatible with Postgres, they can be compatible at various levels. Like I've listed a few of these here. Now the thing is, given all these facets on which you can be compatible, there are differences between databases, as in to what degrees are they compatible to Postgres in each of these facets, right? And that differentiates them. Now there's wire compatibility, which dictates whether you're compatible in terms of byte format, serialization, etc., etc., like the external stuff, right? Do you work with existing Postgres drivers? Then there's syntax compatibility. Do you support the same syntaxes, right? I mean these two are more rudimentary. I don't think much about them, and if you want compatibility, most databases do guarantee these, right? Now then comes the feature compatibility, right? So do you support triggers, stored procedures, things like that? And then finally there's runtime compatibility, which is do you match the exact execution semantics? So if a user were to use your database, like a distributed database and some other data and Postgres, would they be able to find any difference at all, right? So now the thing is, we'll focus on transactional compatibility, and it touches the latter two facets, which is feature compatibility and runtime compatibility in a way. So moving on, now compatibility at the transactional layer is even more important because of certain aspects, right? So you could get away without compatibility in some scenarios by changing your app, but this is even more important because asset transactions themselves are very tricky, right? I guess you all agree with that. And on top, when you want to do distributed asset transactions, it becomes even more hard. Now that's because you have to take care about a lot of things like fault tolerance, there's clock skew, and then you want to automatically shard your data, and then once the shards grow you want to automatically split them, etc., etc. So transactions become hard when you distribute them, right? And given this, there is no way at all an app can change logic to work around this incompatibility in the transactional layer, right? So it's more important to be compatible at the transactional layer is what I mean to say. Now given this, I'll move on to first talk about the new isolation level that we have added, which is read committed. Now Postgres has 4 isolation levels, just 3 actually. The 4th, which is read committed, is the same as read uncommitted is the same as read committed, right? So you see the first 3 isolation levels. Now they are ordered in decreasing order of strictness, and so serializable is basically the strongest, and read committed is the weakest. Now as you go down, you get lesser strict isolation levels, but you get more performance because there's less conflicts, right? So now just keep that in mind, and given that if a user is using read committed or some isolation level which is not supported by the database, it becomes very hard to port the app to the distributed database, right? So hence the reason of supporting read committed and getting parity with Postgres. Now moving on to explain read committed isolation level itself. So there are a few key ideas which differentiate read committed isolation level from the other levels in Postgres. So the snapshot and serializable, I won't talk about those, but the way in which read committed is different is every statement in a read committed isolation transaction works on a new snapshot of the database, right? It works on the latest snapshot. The second key idea is that apps never face serialization errors when they use read committed isolation level. So you never see those 40001 errors, and Postgres does something magical there to handle those, right? So these are 2 key ideas. Now there's a third idea as well here, which is not really coming from Postgres, but we added it. So there's something called read restart errors in Yugabyte. Now these occur, these stem from clock skew, which is inherent in any distributed system. So clock skew is a big problem, and it can lead to funny things wherein a client commits some data and quickly tries to read the data from another location, another node, right? And then the database can be in a ambiguous state as to whether to return the recently written data or not, right? So now different databases solve this in different ways. Some of them try to put tighter bounds on the clock skew by fancy algorithms, and some others just surface the error to the client in terms of read restart errors, like what Yugabyte does, right? So this is a real problem. I'll quickly, in later slides I'll show you how this occurs, etc. But the thing is, the semantics for read restart errors were not defined because Postgres is a single node database, right? It's not distributed. So given this, read restart errors are open for semantics. Now the thing is, we ensure that read restart errors don't occur in read committed mode. Clients don't have to retry those, they don't have to worry about those, right? So that's the third point. Now given this, I'll quickly switch to a demo wherein I'll show the first 2 ideas. So moving to the demo, I have here an instance of YugabyteDB running on version 2.15, and I have 2 open connections to the database. Now what I'll do is I'll quickly create a table with 2 integer columns, one of them being a primary key, and let me insert a row 1,5 here, and now let me start off read committed transactions on both connections, and I'll first do a select star on the first connection. We see the inserted row 1,5, the recently inserted row. Now if I were to insert a new row in the second transaction and commit that transaction, and then again perform a select on the first connection, I would see the newly inserted row as well, the newly committed data, right? So this is the first key idea of read committed, which is every statement is going to read from its own, like read from a new snapshot, right? So given this, hence the name read committed as well. Like every statement should read what was just committed before it was issued, right? Now, given this, I do want to mention that if it were repeatable read, which is snapshot isolation, you wouldn't see this behavior. Both selects would return the same data, right? Now that is because a snapshot isolation transaction uses a single snapshot for all statements, right? And that's about it. So now moving on to the second key idea which we see with read committed isolation transactions, which is apps don't see serialization errors, right? So for example, if I were to now again start two read committed isolation transactions, and let me just select the data on both connections just to keep track of the current state. And now if I were to update the row with key equals 1, like update the value to 15, and then on the other connection I just double the value of v, right? So that's a conflicting write. So you see on the right that this transaction waits because it's conflicting. Now this is going to wait indefinitely for the first transaction to end, right, to make progress. Now this is pessimistic locking actually, which I was talking about. Rob will talk more about it. Now this guy is going to wait indefinitely until the first transaction commits or rollbacks. So let me just commit it, and this thing completes. Now if I do a select on the second transaction, you see that v is 30. This is actually double of 15. It's not double of 5, right? Yeah, it's not double of 5, and that's because to handle serialization errors internally, what Postgres does is when there is a conflict, it rereads, it waits for the conflicting transactions to end, and then it rereads the latest data from that row, and then reevaluates the statement on that row. That's how it handles conflicts. So that's what happened here. It waited for transaction 1 to commit, read 15 and doubled it, right? So that is idea number 2. Now moving back to the slides. So now I'll quickly show what read restart errors are. Explain in detail how they occur, right, and what ambiguity they try to avoid. So let's take a detour. Let's assume I have a cluster here of 5 nodes, right, and I have some clock in this world which is just integers, and let's assume they like increase monotonically. So I have given some time units on these nodes, like n4 as t equals 2, and the rest 4 nodes run on t equals 5. And let's assume that the max clock skew in this world is 8 units, right? So they can be apart by 8 units max. And there's 2 clients here, person x and y, and then there's a key value pair k1 v1 which is committed as of timestamp 0. That's the initial state. Now if at all person x was to do a write to update the key value pair, like let's say he or she writes value 5 for k equals 1 at timestamp 5, and then let's assume that after 2 time units, so you see the clocks have bumped by 2 units, 477. Now after 2 units, person x commits that transaction. So the entry which is written in the database is 1,5 at t equals 7. Again, this is MVCC, right? So we keep history of all records. So given this, given that the person committed at t equals 7, let's assume that after a second, after a time unit, person x gives a phone call to person y and says, hey, I just wrote this data, you can go ahead and read, right? So if that happens, and if person y again after 1 time unit issues a read, right? So here's where the problem comes. So person y connects to a node which sees time as 6. So n4 performs a read at t equals 6. Given that, the database is now confused if at all it should return the row with value 5. Now the ambiguity is because in one case the database might get a read request where t equals 6 is actually from past, like some old transaction, and it's not supposed to return this row. Or it could be the case that t equals 6 is actually in future, but lesser than 7 just because of clock skew, right? So I mean, there's this confusion here, and hence to avoid breaking any guarantees, we return a read restart error, right? So this is done just so that clients always read whatever they have committed, right? They should read no less. So let me show this with a demo. Yeah, so I have a cluster here again on 2.15, and I'm going to create a new table test. I just dropped the old one, right? So the key now is going to be serial key. That's the only difference. And then I'll create another table test2 with the same schema. Now I have two SQL files here. One of them inserts a new record into the table test every second, right? So this is just repeated writes, right? And then I have another file which does a read. Actually, I have two files. One of them does repeated reads in repeatable read isolation level, and then the other does in read committed isolation level. So let's just see repeatable read. So I start a transaction. I issue an insert into table test2. Now this is just done to start a distributed transaction, right? And then the next statement actually does a select, which mimics the read from person Y. So I'm expecting read restarts to occur in this statement because I mean there can be ambiguity at times. And then I just commit the transaction. I just do this repeatedly, and I have kept it simple and not used procedures for simplicity. So what I'll do now is I'll start the write workload, and then as you can see, if I start the read workload in repeatable read isolation, we see read restart errors. Now I mean it's rare, but you do see them, right? Now if I were to do the same with read committed isolation level, you would see no read restarts at all, right? And if you see this, there are no read restarts. So yeah, this was the demo. Now let me switch back to the slides now. Now there is some roadmap for read committed. I mean you can see the progress etc. here, what future enhancements we plan to add etc. etc. So I just added this here, and you can also check what releases have what finer pieces, right? So you can see that as well. And then finally these are the docs for read committed isolation level. Again, this is in beta, so you see the tag on top. You can click on it to see what beta means actually. Yeah, thanks. I'll just pass on to Rob now.
All right, thanks Piyush. Now, one of the pillars of Postgres compatibility that we're introducing in YugabyteDB is pessimistic locking, which Piyush touched on earlier. So I want to dive a bit more into that here. And like read committed, it's a very deep topic, so we'll try to give you as broad an overview as we can with the time we have. And just a quick glance at optimistic locking. It's a strategy for dealing with contention in transactional databases, whereby conflicts are resolved by immediately rolling back some set of conflicting transactions to allow the others to proceed. And a very immediate benefit of this approach is that you never have to worry about deadlocks. Since no transactions are waiting, there can't be any deadlocks. But the price you pay for that convenience is potentially significant, where you might roll back transactions unnecessarily, especially in high contention workloads. And moreover, it's just incompatible with Postgres behavior. So what does Postgres do and what does Yugabyte do? We use pessimistic locking, where we deal with conflicts by forcing transactions to wait. So this waiting behavior allows us to defer rolling back conflicting transactions until it is absolutely certain that a rollback is necessary. If the earlier transaction, which caused a transaction to wait, is rolled back, then the waiting transaction can now proceed without conflict after waiting. So let's see that in action in Yugabyte. I'll just create a very simple table over here. It's key and a value. I'll insert some data. And on this transaction on the left here, we'll update a row where k equals 5. And then on the right, we'll update row 6 and then try to read row 5. Now we see that it blocks. So this is the waiting behavior we were discussing earlier. And if we now commit on the right side, we see a serialization error. So that's great. Now, what happens if we roll back? Let's go over that real quick as well. So let's say we again update the same row. And now on, on the right side, we update another row. And then we try to read the row that is being updated on the left side. And let's see, when we roll back, the right side is unblocked and is able to proceed without conflict. Great. Now, let's make things a little bit more complicated. So on the left side, let's say we update this row 8. And we next try to read row 6, which has been updated on the right side. Notice the right side transaction is still open, so it still holds this lock, and so the left side is blocking. If the right side were to attempt to update a row which is locked by the left side, we see immediately that one of the transactions is rolled back and the other one is allowed to proceed. And this is because we detected a deadlock. Great, so let's talk about deadlock detection. And it's worth saying that detecting deadlocks in a distributed setting is not super easy. So we need it to happen quickly. As you saw in the demo, it happened immediately, but in Postgres, it'll trigger after a second of waiting. We need detection of deadlocks to be guaranteed anytime a deadlock is created. And so we lean heavily on the concepts and methods in this paper, which you should check out. It's a wonderful paper. And it introduces two concepts, which I'll talk about here. One is the wait for graph. You can think of this as a graph with nodes being transactions and edges being directed edges, indicating that one node is blocked on another. And another concept is probes, which are messages sent from a waiting transaction through the wait for graph. And so let's look at, and those probes are trying to detect cycles, so trying to come back to the originator. So let's look at what that looks like. So we have 3 tablets here. Transaction 1 is blocked on transaction 2 at tablet 1. Transaction 2 is blocked on transaction 3 at tablet 2, and transaction 3 is blocked on tablet 1 at tablet 3. So from a bird's eye view, clearly we have a deadlock here. But what's interesting is how do these distributed tablets, which could be on different tablet servers or in different regions, coordinate and detect this deadlock in Yugabyte. So each tablet will send any information it has about a waiting transaction to that waiting transaction's coordinator. So coordinator 1 is coordinating for T1, and it gets the message that T1 is waiting on T2. And likewise, these transactions end up at coordinator 2. So from coordinator 1, we send a probe with a probe ID saying, hey, T1 is waiting on T2. We send that to the coordinator for T2, which we know to be coordinator 2. And coordinator 2 looks at its own local wait for graph and says, okay, T2 is waiting on T3. I'm managing T3. T3 is waiting on T1. And T1 is managed by coordinator 1. So I'm going to forward this probe back to coordinator 1 with the same probe ID. And when the original coordinator gets back the same probe ID and the blocking transaction is the same transaction which originated that probe, we know there's a cycle in this wait for graph and therefore a deadlock. So that's essentially how deadlock detection works in Yugabyte. And leaning on this method from this paper, we get minimal overhead. So we need constant additional memory per, and only to send one probe per conflicting transaction. Obviously, probes could trigger many RPCs if the graph is complex, but that's sort of an inherent complexity that we can't do anything about. So that was deadlock detection in a nutshell, pessimistic locking in a nutshell. And if you want to dig into this more, you're welcome to check out these additional resources for read committed, pessimistic locking, and a roadmap for more generally what is on the way in terms of Postgres compatibility. But otherwise, thank you for joining us and listening. And please, if you have any questions, share it now.